thing is, I owe you this example. So I actually thought through this for a period of time, and yeah, and I find that maybe I would be more comfortable with this approach. Okay. So in the earlier example, we have, assuming that we have the maybe just bit of context. Bit of context is how many. The question is if the size of a node is 4K and the size of a search key is 12 bytes, the size of this pointer is 8 bytes. Okay, so the question is how many lookups do you need to transfer? So I think I'm more comfortable to think about it in this way. Okay, so in a single node, you have 4K. The data is 4K. Excuse me. But this consists of various pointers and key. And if let's say we assume that there are n number of keys, there will be n plus 1 number of pointers. So this is the assumption. This is the assumption. So what we will do is we will have n number of keys. So it will be n times each key has 12 bytes, so n times 12. N plus 1 number of pointers, so this is times 8. And this will be equals to 4 times 1024. And if we solve this, we get n equals to about 204.4. So this single node is able to carry 204 keys and about roughly 205 pointers. Actually, yeah, actually it's better if I put down n to be 204 keys and 205 pointers. Yeah, I'm going to change this. Yeah. So I think this is a better way to put it. Yeah. So the tree has 204 keys and 205 pointers. And if my tree has 205 pointers, it means that the fan out is 205. So 205 way fan out. If it's a 205 way fan out, what we should do is we would have to do a log of 100 million base 205. I think this is going to give us 7 point something, which we are going to see it. Okay, so this is how we solve this question. Okay. Actually, this question really is more like what is the number of fan out factor in my tree? That's the first thing. And the second thing is, what is my height of my B plus tree, which is my H. And this is how we calculate log of the nodes base the fan out factor is how we calculate the tree. Can? Okay, so this is the first point I would like to make. Yeah, I'm going to close this one. Oh, never mind. Never mind. The second point I want to make is the following. So that was the second example. This example, yes. So this example. So I remember I cleared it up just before the end of the lecture last week, but I did not correlate it back to my slide 7 and 8. So I will correlate it now. So what happens is that I think this is a index nested loop. So what we really want to bother about is for index nested loop, what is the cost? Okay, so let's not think about how the formula works first. So let's ignore all the formulas first. Let's just think as an intuitive manner for index nested loop join. How does it work? Excuse me. For index nested loop join, it says that the student is on outer table, outer loop, and the text is on the inner loop. Okay. The number of transfers is easier to see. If you look at the number of transfers, we have seen that for nested loop join, the number of transfers on here will be equals to the number of blocks on my outer loop. So this is equals to the number of blocks on my outer loop, which is equals to 100. Okay, so this is slightly easier to see. If you look at this one, this is in fact the number of times I need to find the index. And the number of times I need to find this index will be the number of records in my student table. Because for every single record there, I need to do an index search. Okay, so you notice that it is actually not this one. It's a bit not very intuitive, but if you think about it, it makes sense because I'm joining I'm matching between let's say for example I have two holes to put the screw in, right? Then I have 5 screws. Then I match the screw to the screw hole, right? I only need to match the number of screw holes that I have. So it's a similar example, although maybe a stupid example, but it's a similar example. So I'm matching the outer loop, which is the number of students. So every student in my outer loop, I want to map it into an index search to the corresponding rows in my text table, which is why this is 5,000 over here. And what we have is for this 5,000, we have the fan out factor to be 20, and as we have seen earlier, so it's 20 over here. It is we use log of the number of records base 20. This will be the number of the height of the tree. Okay. So typically we have one more. In this case, the reasoning is that we may need to do one initial search from, in this case, they call it the master file. So this is an addition of 1. So for every single record of my students, it needs to traverse through 5 levels. Okay. So this can be considered to be like your leaf, and this can be considered to be your height. Okay, this whole thing can be considered to be your height. Okay. So this is what it is. Okay. Okay. So for every record, I need to, this is the cost that's being incurred of transfer. Similarly for the seek as well. So, okay, so last week or Tuesday, when I was going through this, I was also a bit confused. This formula, why is it like so different from what this is? So I was very confused during that time. But actually, they are the same thing. Why? Because like this has this time, but this formula doesn't put the time. Okay, so what this is saying is that this is both the seek and the transfer. So if let's say, right, the easiest to illustrate is that, let's say this is a unit time, this is a unit time, this will be equals to BR plus BR, which you notice is equals to this one. Which equals to this. Okay, so actually this is exactly the same as this part. Okay, sorry. Okay, the next thing is NR times T. Okay, again I was quite confused. Why is this like that? But actually, if you notice, NR is actually this thing. Okay, is exactly the same as this. And C is the cost of it going down one single block. Okay, so this C is the cost of it going through one block, which is equals to these two together, which is the seek and the transfer time. So if you notice that this NR corresponds to this 5,000, this C, which they abstracted it to be the cost of a single selection, which is equals to the seek and the transfer cost illustrated here. So actually these two are talking about the same thing, just that the way it is being written seems to be very, very, very different. Ken? I hope this is clearer now, how these two slides correspond to this slide. Okay, if there are no other questions, give me some time, about 10 seconds. I'm going to turn off my WhatsApp because quite irritating. Yeah. Okay, so I'm going to share my screen. Sorry, that was a colleague. Yeah, so she wanted to discuss about. Yeah, so there's some issue came up today. Yeah, so but I told her that I'm teaching already, so it's fine. Anyway, I turned off already. So last on Tuesday we were here. So we were discussing on this. How do we find the number of merge passes that's required? So recall that we went through the cost analysis of the merge sort. So this is the cost analysis. The first thing that we want to do is at the very first stage, we have when we are creating the runs, we read and write every block. So we have 2 multiplied by the number of block transfers. The number of runs that is created is the number of blocks divided by the number of blocks that can be held in memory. And then again, we do the log. This is similar to the how to say your normal tree height of the tree algorithm. And for every block, every pass, you do your read and write again. And then you just add all these together to get this formula over here. Okay, so this was something that we went through last week, or rather on Tuesday. So we had this example, and I remember I asked you all to calculate it yourselves. So let's go through this once again. So M is the number of blocks in the memory. So memory size is 40 million. And the size of one block is 4K. So I'm going to use the easy, not easy lah, but the cheaper method, to do it. Okay, so so that I can I can just do equals to 10 times 10 to the power of 6 equals to 10 to the power of 7. Okay, so this is the number of blocks that is sorry. This is 10 times 10 to the power of 3 is 10 to the power of 4. This number of blocks in the memory that is available in the memory. So number of blocks in relation will be equals to 40 times 10 to the power of 9 divided by 4 times 10 to the power of 3, which is equals to 10 times 10 to the power of 6 equals to 10 to the power of 7. Okay. So okay with this calculation so far. So number of merge passes, we use the formula, which is the ceiling of log m minus 1 BR divided by m. So BR is 10 to the power 7 divided by m 10 to the power 4. And this is the number of blocks that can be held in memory. So this is log 10 to the power 4 minus 1 10 to the power 3, and this is the ceiling. I think this is equals to 1. So only one merge pass. Okay with this? Okay, so I went through this last week. So this is A. Let's look at B. So B is find out the disk transfer cost of sorting the relation in seconds. So let's see how much. So in order to do that, okay, let's look at this. So the cost it needs to transfer a block is equals to this. So this is the cost, 2 times BR times the formula. So cost equals to 2 times BR times the formula on top plus 1. Sorry, I should have put it down here. Okay, so this is the cost for this is the amount of this is the cost for the transfer, which is the amount of blocks. So this is the number of blocks, which is equals to 2 times number of blocks in relation is 2 times 10 to the power of 7 times this equals to the answer on top, which is 1 plus 1 equals to let's see 4 times 10 to the power 7. Okay, so this is number of blocks. Okay, so the block size is 4K, and we know that the disk transfer rate is 40 million per second. So the time to transfer one block will be equals to 4 times 10 to the power of 3 divided by 40 times 10 to the power of 6. And this is going to give me equals to 10 to the power of 3 divided by 10 to the power of 7 equals to 10 to the power minus 4. So this is the number of blocks that's going to be transferred this is the time it takes to transfer a single block in seconds. So this transfer cost will be equals to 4 times 10 to the power of 7 times 10 to the power of minus 4 equals to 4, 3, which is 4,000. Okay. Any questions with this? All good? Okay, very good. Okay, let's look at the next example. Sorry, this answer. Yeah, let's look at the next example. So maybe you all take about 3 minutes to try to solve the first one. The block nested loop join. So the first thing you want to find is find number of blocks. Of R1 and R2. So that would be the first thing. So I'm going to select R1. Yeah. So for R1, it has 20,000 block, 20,000 tuples. R2 has 45,000 tuples. And 25 tuples of R1 fit into one block. 25. Then 30 tuples of R2 fit into one block. 30. So the number of blocks for R1 will be equals to 20,000 divided by 25, which is equals to 400. Yes. And this is so 800. 800. And this will be equals to the 1,500. Okay, so this is the very first thing that you want to do. The next thing you want to do is you want to find a block nested loop join. So assuming if R1 is the outer loop, so R1 is outer loop, so 800 will be that on the outer loop. And for the inner loop, for every single block of the inner loop, you have to do the outer loop again. So for every single block of the outer loop, you have to load the inner loop. And so this is the number of block transfers in the worst possible case for R1 join with R2. Okay. Okay. The second one is the merge join. Over here, they never state what is M. So your answer will be in M. Okay. So they never state what is M. So we will give the answer in terms of M. So I give you a hint. You will take the next 3 minutes or so to do this. You find out the merge. So we're doing a merge sort of R1 and then we're doing a merge sort of R2. Okay, so you find the cost of this, use the formula, and then you find the cost of this, use the formula. So you find it independently first in terms of M. Okay, so maybe you take you'll be just writing out the formula only lah. So maybe you take the next maybe 2 minutes to do it. The formula, which is this one. Okay, this is the formula to use. And you put it in terms of M. So maybe I'll start in about 1-2 minutes like that. Oh no! Oh. Okay. Sorry, I thought I forgot to record. Sorry. Bit too drama today. Okay, so I will start. Actually, you just use this formula and plug it in, then you got answer already. So for R1, it is 2 times 800 log of M minus 1, 800 over M plus 1. And the second one is 2 times 1500 log M minus 1, 1500 over M ceiling plus 1. So that's all. So this is the merge sort cost of R1. This is the merge sort cost of R2. And then there is a join of both, which is equals to the number of blocks of R1 plus number of blocks of R2 and times 2 because it's a read and a write. Okay, so yeah. So the entire cost of the merge join will be this plus this plus this. Okay. Okay. There's error here. I should have placed a times 2 here, but I didn't. So I will fix it now. Okay, so if you see that in your notes, please fix it. I believe I should have a times 2 here because it's both a read and a write. Okay, let's go for one last example. So write an efficient algebraic expression that's equivalent to this query. So okay, so this is how the algebraic expression would look like if I want to make this efficient. Okay, I'll be frank with you. This is not the best question to have. So typically, you have a few follow-up questions before you come to a question like this. But let's do a very simple assessment of what this expression is trying to say. So this is going to be a selection, and then after that it's going to be a join, and it's going to be a selection, and this is going to be a branch, selection, sigma, branch. Okay, so this is how I draw this query out. Okay, to be frank, it is quite hard to not say quite hard, but from going from here to here, it takes some practice and some effort. Not reasonable for you to write it out like that, just like that. Typically, what a question like this, right? The first step they ask you to do is, from this expression, can you draw out what is the possible so-called algebraic tree or not? So typically for this, what you may do is that you have this branch name, and then you are going to have a join, and you have maybe you have conditions here, and a branch city, and then you have T, and then you have S. Okay, so typically you, from this first tree, you may get something that looks like this. Then the next question will be, how then do you optimize on this tree? Then that is the point whereby you can say, oh, you will use some of the relational algebraic rules to say that, oh, I can push my asset down, because here to this, if I want, I can push my set down here, and I can push my set down here, and I will, but before that, what I can do is I can say that the branch city is Brooklyn first, so I first push down my Brooklyn asset, so it'll be here T. I can first push down my Brooklyn here, because this doesn't affect the rest. So I can push this down first, and now I have asset over here. Then this is the first step. The second step is then I can push down the asset on or my pi asset on both sides, and then I will end up with this expression over here. So getting from this, which is the initial query, to here, actually takes a few steps and quite a lot of effort. And we have not yet fully covered this part for this lecture, and we will be doing more of that in the next lecture, which is after the break. Okay, so are there any questions that I can help you all with for the time being? If there are none, right? Janice, are you here?
Hi, yes, I'm here.
Hello. So welcome to CS211.
Thank you.
Nice talking to you. Hope you had your dinner already.
Oh, yes, I did.
So yeah, so the students are here. Please remember to mark your attendance. Anyway, Janice, you have something to share with them. I told them that you'll be coming in for the surveys already, so they're all ready. They're all kind of ready. Yeah.
Okay,
so,
good.
yeah. Please share with them whatever you need to do. Thank you.
Okay, thanks. I need to share screen though. Thank you.
So you start. Thank you for coming back. And okay, let's look through this will be the last lecture on relational algebra. We'll see how far we can go. I'll try to finish this today, but if we can't, we just have to use next Tuesday. Why? Because I really hope to go into the MongoDB stuff. Okay, let's start. Okay, so query optimization is something that we have talked about just now only. Like we have an expression. So typically we have a so-called relational expression. We draw the relational tree, and then, excuse me, different ways of interpreting the relational tree will generate different costs to it. So yeah, so we want to find out which is the query plan that will generate the least cost. Okay, so we have talked a little bit on this earlier. So we have 12 rules in total. These are the rules to help us to know that one relational algebraic expression is the same as another one. Okay, we will be, there are 12 in total, but we only focus on the first 8. The last 4, we will not do that much. Yeah, so yeah. So let's look at the first one. The first one says that the selection, if it's a conjunctive, which is an and, they can be deconstructed into different a series of individual selections. So this is so if regardless if I select theta 1 and sorry, theta 2 followed by theta 1, it will be the same as me selecting both theta 1 and theta 2 together. And of course, this is related to the second point, which is regardless if I do theta 1 or theta 2 first, that it doesn't matter if I do theta 1 or theta 2 at all. Okay, so these two are pretty intuitive. Let's look at the third one. In the third one, it says that only the last in the entire sequence is required. The rest is not important at all. It's only the last one is sort of required lah. So of course there's a condition, which is the last one must be a subset of those that are in the middle. Okay? So this is so it makes sense lah. So if I am projecting, let's say I'm projecting department name and IC, and after that I project department name. After I project department, then in this case, all these actually don't need. I just need this one. The condition, of course, the condition is that department must be within all of the intermediate operations. Okay? And if I have a selection here, I probably won't be able to do this so easily. So this selection will actually, I can only reduce up to this selection operator. Okay. What this means is that if I have this, so theta department name, I cannot remove all here. I can only remove up to here, and I will have department sigma of this. Okay? So I cannot go all the way in. Okay, let's look at. So this is that. Let's look at the fourth condition. Selections can be combined with Cartesian products and theta joints. So if I have a selection operator, I can push in to make it into a theta joint. This is what we did just now, right? We did that. We have a theta joint and we push it to a selection. So yeah, so this was what we did earlier. So if I have a selection here, I can also push it to become a conjunctive selection. Okay. Okay, let's go on. Theta joint operations are commutative. So E1 joined with E2 is equals to E2 joined with E1. So it doesn't really matter. Okay, so this is quite okay lah. So let's look at 6a. Okay, natural joint operations are associative. So E1 joined with E2 and the resultant joined with E3 is equals to E1 joined with E2 and E3. Okay, so this is the same. So what this means is that if you look at the tree, at first it is E1 joined E2 followed by E3. Similar, this is exactly the same as E2, E3 join first, and then after that the resultant join with E1. Okay? So they are both exactly the same. Also, quite intuitive to know why. Yeah, so I hope this is clear for all. So I won't go into detail this one. Okay, This one may be a little bit confusing. Okay. E1 join with E2, and this resultant, this theta join with E3 on theta 2 and theta 3. This is equals to E1 theta join with I should say this. This equals to E2 theta 2 join with E3, and then join with E1 on theta 1 and theta 3. Okay. So the theta 2 involves attributes from only E2 and E3. Okay. So this one is a little bit like confusing, a little bit confusing. So let's see what this actually means. Okay, so this means that if I have a theta 2 condition, this theta 2 condition has attributes from E2 and E3, and this theta 3 condition has attributes from E1 and has attributes from E1, E2, and E3. I'm able to pull out this theta 3 condition to the outside. E2, the theta 2 has only attributes from E2 and E3. And so theta 2 is unable to move out. Because if I move this out, then this will be an empty null set. Okay. So theta joins can be associative in this manner, whereby if theta 2 has attributes only in E2 and E3, this has got to stay. But theta 3 can be taken out of the joint. Okay. So this is something like E1 theta 1. Yeah, I hope this I hope this will make it a little bit clearer. E2 and then theta 2, theta 3, E3. So this is actually equals to E1 theta 1, E2 theta 2. Correct. This is because of this condition. And then because if E2 has only attributes from E2 and E3, E2 has got to stay here. But if I want, theta 3 can come out. Okay. So this is the one that is a little bit more confusing, but still not too bad. Okay. I'll go on to the next. Okay. So the selection operator distributes over the theta joint under this condition. So this is a selection operation. If the theta contains only in E1, I can push my selection operation inside. And to be frank, if you can do this, typically you will do this. Why? Because what this will mean is that I'm going to have a smaller table here. So this table is going to be smaller, and when this table joins with E2, the result is still going to be the same, but the cost is going to be smaller. So typically, I want to push my selection in if it's possible. If I can, I also push my projection in if it's possible as well. So that's the typical heuristic. So if possible, push your push your selection in. If possible, push your projection in as well. So in this case, if theta naught contains only attributes of one of my expression, I can push it in. Okay. Okay. So okay with this. Okay. So let's look at this is 7a. Let's look at 7b. When theta 1 contains only attributes of E1 and theta 2 contains only attributes of E2, then we can push it in individually in this manner. So this is how to say, this is a corollary from 7a, very similar to 7a, but these individual ones I can push this in. So let's say I have theta so this means that I can do this. So this means I can do that. Okay. And what was I going to say? Yeah, okay. So, but you must remember, this is a selection operator. Okay. Can I do this? Can I do this? What do you guys think? And same thing, theta 1 only contains attributes of E1, theta 2 only contains attributes of E2. The answer is cannot. Why? Because if theta 1 only contains attribute of E1, theta 2 only contains attribute of E2, then this, for example, this is let's say this is department and this is name, and let's say this is join on ID, right? Then this is becomes this is only one column department. This is only one column name. Then this join this, there's nothing to join. And then this will become a null set ability. Okay, so remember this only applies to selection, not to projection. Okay, so yeah, so that must be careful in this. Okay, cannot. Okay, let's look at the next one. Equivalent rules number 8. Oh yeah, so 8 8, 9, 10, 11, 12 I will not go through 8 onwards because yeah, this one are not as important. So the earlier ones are the ones that are a bit more critical. 1 to 7. Okay, let's go on. Okay, let's look at one example of this transformation. Okay, so if let's say I have this relational algebraic expression, I am let's see what this is trying to say. This is a selection of the name and title where I have a instructor from my department of music that teaches or all the course titles which the instructor from Department of Music teaches. Okay, so this is what this expression is trying to say. So I want to extract out all the course titles which is taught by all my instructors from the Department of Music. Can? Yeah, so this is what this is trying to say. Cannot? Okay, so right now we have, if we, okay, I give you 1 minute to draw the tree out for this. Okay, so okay, let's do it together. So it should be like this, like this. Sorry. And like this. After that, like this. Like this. So this is this expression. This tree is this expression here. Yeah. So during the exam or what, you remember to write all your things down. So now a bit hard, but you have to write all your things down. Okay. So this is the initial one, and you realize that probably this sigma should be able to push down. Okay, so we probably can push down this sigma somewhere. So let's see how, and we are actually quite sure that this sigma should be pushed into the instructor because only instructor got this sigma. So there's no other place to push this down to lah. So yeah, so it's quite obvious in a way that we are going to push this into the instructor. Okay. So if you want to push this down, what this looks like is that this is a sigma, and this is of E1 join with this entire expression, which is like E2 lah. So we can abstract it to be like this whole thing is E2. And if we use law 7a, theta, this has only attribute in E1, so this can be pushed inside to form this, like this. Okay, so this sigma will push to do the selection on the instructor operation first, followed by doing the join operation. Okay, so if I were to draw this out now, this is going to look like this. Okay, this is going to look like this. Okay. Okay, look. So this is the first example. Okay, okay, then how I got here? Very good. Okay, let's look at the slightly more complicated one. Okay, so this will involve multiple transformation. Okay, maybe you take 1 minute to draw out the tree for the first expression. So this is how this looks like. Okay, so I first have the pi on my course, then goes to teachers. The teachers join with the instructor. Thereafter, it joins with there's a selection on based on music and the year, and then the projection. So this is I want to find in English. This is I want to find the name of the instructor and also the title of the course of all my instructors from the department name of music that taught a course in 2009. Okay, so here we have oh, sorry. Here we have two conditions. The conditions is music and year. So what we want to see is okay. So but then we also find that the teachers is quite deep down. You see, it's quite deep down. So this is here, but this is quite deep down in into the second drawing expression. So what thing that we can do is we can try to see whether are we able to push this deeper so-called table slightly higher up or not, so that we will be able to easily push our selection operator inside. Okay, so the first thing we do is we remember we have the commutative so-called attribute, which is law 6a. So instructor join with teachers join with this expression will be the same as I do the join between instructor and teachers first, and then they join with this. Okay, so this using law 6a will look like this. And in the exam, you have to write out what law that you're going to use. So very important, you have to write out the law. Okay, so if I want to draw this, is going to still look a bit messy, but it will be a little bit better. Instruct and teach, and this is pi and cos. So this is how this looks like right now. Okay, right now we will see how we can push in our sigma inside. Okay, in this scenario, what we'll do is we will use this condition to okay. So okay, let's say this this is actually able to push this into our individual tables within my join condition. And how we do that is using law 7a. Okay, in law 7a, it states that if one of my so-called condition affects just one of my tables, I'm able to push that in. So in this case, this entire condition, right, it affects only this part of my join. So it doesn't affect this part of my join. So what it says that because in this part of my join, this course does not have department name. Oh yeah, course does not have my year. Let me see. Instructor course. department name is here, course, let me see, department name is music, instructor. Okay, so year is over here, course is here, but let me see. Oh, it doesn't affect here. Why? Because right of the projection. So my course, my department name is not here at all. So it doesn't affect this part. Can you see this? It doesn't affect this part because department name and my year is only in this uh, expression. So it does not, it's not in, it is in course, but I have already done the projection here. So the department name is not in this entire thing at all. So it does not affect this part of the expression. Can you all see this? So because it will not affect this, that's why I will be able to push my this sigma down one level to have this. Okay. Can you see? Can you see how this was done? You know, so because both is not in my this part of my join, okay, so I can push my selection down. Okay, let's look at the next part. We're not done yet. Okay, we're not done yet. So this is what we have just now. So this is pi, and this is a join, and this is sigma, and this is a join of instructor teach, and this is the pi of course. So this is what we have the last one. So what we have now is I have the sigma of two conditions, the department name and the year. And well, now what we do is that we are now able to push. Okay, so department name affects only the instructor. Year affects only the music. Okay, so in this case, what they did is that they actually did it step by step. So they have you can from this you can use the break up this conjunctive operation into department name and year first to form this expression. Can you see can you see how we got this this part? This part should be easier to see. That I'm just breaking this end up into a bracket, that's all. Okay. And once we come to this expression, we now realize that theta year affects only the teachers, theta music affects only the instructor. And so we can use law 7a two times. We push one time, and then we use the law 7a again. We push this another time to form this expression. So this entire thing will replace the entire first part here. So what we will have is we are going to have this pi directly with a join, and this goes into a pi and cos, and this goes into a join with a sigma and a teach and instructor. Okay. Are you all following? I hope you are following, because yeah, if you are not following, you let me know. Then I will try to explain again. Okay, very good, Mr. Sean. Thank you. Okay, let's go on. Okay, so so we have the transformation. Yeah, so I drew for you the entire transformation. This is the initial one, and then in the end it become like this, which was I hope that was what I drew in the last one. Okay, so yeah, so typically this is something that you will need to be able to do. So you want to push all your sigmas into the tree as much as possible. Okay, I have another example, I think. So this is the other example. So okay, in this example, what we have is we do a project. So earlier we did more of the selection. Let me see. 7B, what's 7B again? 7B is selection. Let me see what is happening here. Why that? Maybe it's not 7B. Let me see what it should be. It should be 7B. No, 8. 8. 8, but I say 8 don't study. Yeah, maybe I should say 8. Okay, wait, let me see what's happening here. I am pushing in my projection of yeah, actually sorry, this is 8. Yeah, so I think let me see, is it 8? Can I use others to explain this? Yeah, I think this is 8. Yeah, this is 8. I think this is 8. I thought this is 7, but apparently this is not correct. Yeah, sorry. Yeah, let me try to see what this is. So in this scenario, this is about a transformation whereby I actually require only the name, title, uh, on uh, so-called on the outermost layer. So what this example is trying to say is, if let's say this gives me this table, in order to make it so-called a little bit smaller, what I can do is I can carry out one projection on my this condition, on my this resultant table, so as to make my intermediate table smaller. And of course, there is a certain condition that comes to that. The condition is that the join condition must still be there, which is why the course ID is still here, and the name must still be here as well. Okay, so because these are the ultimate resultant that you're going to extract this from. So I hope you can understand. So in this, what is happening is that although I'm going down this step, the the number of records here, or rather the number of columns here, may still be very large. So I can do one additional step of reducing the size of this by doing a projection before doing the drawing. But then the question then is, what should the projection be? So the projection should then we have to look at what is the ultimate thing we want to project. So an easy way to see is that we have to this pi condition. Let's say if this is let's say this is condition R and this is condition T. We have to R minus T, but I have to plus the common attributes where you do the join. Okay, so yeah, so whatever that is not here, or whatever that is here that is not here, has got to be in this projection, and we need to include in the natural join conditions attributes there also. Okay, I cannot remember, I cannot find out, I will find out for you what is the right law for this. I can't, yeah, I thought it's 7a. So when I was preparing this, I thought it's 7a, but now apparently it's not 7a. Yeah, it's not 7a. So I think it's 8. I think it's 8. Yeah, now I see, yeah, I think it's 8. I think I should have went over 8. This is 8a. Yeah, I think it's 8. Now I see, yeah, I think this is 8. Yeah. Okay. Sorry, if you don't mind, I would like to go through 8a, if you don't mind. Sorry, that I backtrack this part. So 8a says, sorry, I'll go through 8. 8 says that if I have E1 and E2, and if my theta affects only the attributes from L1 and L2, where L1 is attribute from E1 and L2 is attribute of E2, I can do my projection independently. Okay, so if I have a projection based on just the E1 table, and I have a projection based on the E2 table, I can break out this projection and I can push this projection inside. Okay, sorry for backtracking on this. Yeah, so I thought this one don't need, but yeah, I misread. Yeah. Okay, follow this one. Okay. 8b is a little bit complicated. In 8b, what happens is that I now have 4 conditions: L1, L2, L3, and L4. Okay, now I have L1 and L2. They are the common attributes of E1 and E2. Okay, and L3 is those that are involved in the join condition, but they are not in L1 and L2. L4 is those that are in the join condition, but they are not in L1 and L2. So it is the common attribute between E1 and E2, because they are involved in the join condition, but we are not going to project them out ultimately. Okay, so for example, if I am doing a projection of department and name, and E1 has department and ID, E2 has ID and name. Okay, what is L1, L2, L3, L4? L1 is going to be department. L2 is going to be name. Because ultimately I want to project out name and department. L3, what about L3? L3 is involved in the join condition, but they are not in L1, L2. So the only attribute left is ID. And L4 is also in the join condition, but it is not in L1, L2. So L4 is also ID. So this scenario allows you to push in your projection into my individual tables before they are being joined. Can? Okay, I hope this is clear. Okay, I'm very sure 9 to 12 you don't need to know. And now I'm very sure that this is using 8B. Okay, I hope this is clear. Sorry if I confuse a little bit here and there. Okay, let's look at the next one. Okay, so the next one talks about the join order. So in this, I have two different kinds of algebraic expression. So the first is join between R1 and R2 and then R3 versus R2 and R3, then join R1. So this is an example of what the two may look like. Okay. Later on, we are going to calculate that there's a heuristic that we can apply to this to say that which is the order that is more so-called preferred. Okay, but for the time being, just keep in mind is that whatever join condition or join order that we have, they will have a slightly different cost. Okay. Next, okay, so these again, there are two representations of the same thing. This is instructor join with the projection of course and teachers, and this one is I join between the teach and course first, and then join between this one. So both, they're all equivalent, and what happens is that there's a so-called enumeration of this kind of expression in your database whenever a query is being done. The thing is, it is extremely expensive to list out all the possible scenarios in your that is there. So so I'm going to say it's actually impossible to give out all the scenarios. Later on, I'll be showing a formula how we can calculate that, but the cost is too much. So in order to reduce that, we use certain heuristics to help us to understand how do we calculate these so-called which expression tree do we actually go for in doing the execution. So I will not go through this part. So let's say there are two expressions. We want to find out what is the so-called cheaper expression. So again, this one I will not go through. All these are relating to the enumeration of equivalent expressions, which actually we never study, but actually this can be done with dynamic programming. But having said that, what this slide is just trying to say is that there are similar sub-expressions that are repeated, and so if we store them up, it can be stored. It can be solved later on with dynamic programming. Yeah. So, but we will not go into that in this module because we'll not go into that. But we will use statistics to determine the cost. And these are the stats that we will go through here. You get again the number of tuples, the number of blocks, the size of tuples, the number of tuples in a relation that fit into a block, which is F. Okay, V is the number of distinct values that appear in the relation R for attribute A. Okay, so V is the number of distinct values that appear in relation R for each attribute A. So if A is the key, so there will be n distinct values that appear. So for example, if this is the table so-called faculty, and I have ID, and the faculty size is 5,000, my V of ID faculty will be equals to 5,000. The number of distinct values that are there. If department, department, if department, if there are, let's say 10 departments, so my V department faculty equals to 10. Okay, so this is how we determine these values. So if tuples of R are stored together physically in the file, then B, which is number of blocks, equals to F. Yeah, so this one we have studied before already. And stats about indices, height, so rather these are all heuristics that we use. Indices, heights of the B plus indices, number of leaf pages. Yeah, so these are all heuristics. Okay. This one, okay, let's go through one and then I will stop for today. This is an equality operator on attribute. So equality operator on attribute, you would imagine that let's say if the attribute is a primary key, what is the possibility of choosing this? The probability of choosing this is going to be 1 divided by the size of my table, and also which is the number of distinct values of that. Okay, so if let's say this one shouldn't be n, now this should be 1, sorry. Let's say if the A, right, department equals to CS, and there are 10 departments, so the probability of that is going to be probability of that is going to be, probability is equals to 1 divided by 10. This is the expected number of records to be extracted out will be this one multiplied by n, which is v n divided by v. So yeah, this one is expected number. Yeah, so this is correct. This is expected number. I thought this is probability, yeah, but this expected number of records returned. Okay, the probability of the record being selected is 1 divided by v over this. Okay, so the time is now 10:10. Okay, I think I'm going to stop here. Thank you so much for your time this evening. And I'll see you again next week, Tuesday. I still have 10 more slides here. Yeah. Thank you so much.